we can get started. So welcome everyone to this week's Autonomy Talk. This week is a great pleasure to have with us Professor Pierluigi Nuzzo, who is the Kenneth C. Dahlberg Early Career Chair and Associate Professor of Electrical and Computer Engineering and Computer Science at the University of Southern California. So something about Pierluigi. Pierluigi comes from Italy. He obtained a Bachelor of Science and Master of Science degrees from the University of Pisa and the Sant'Anna School of Advanced Studies in Pisa. And then he moved to the US, where he got his PhD degree from UC Berkeley. He held positions at the University of Pisa and IMEC in Leuven in Belgium, where he was working on mixed signal integrated circuit designs. And his research interests in his groups focus on computer-aided design and verification methods for safe and dependable autonomous systems, automated generation of assurance cases for system certification, and analysis and design of secure and trustworthy hardware platforms. As you have seen, he has won many awards for his exciting work. And today he's going to talk about contracts for trustworthy autonomous cyber-physical systems, which is kind of the hot topic he's working on, and that I find very interesting, and I look forward to hearing more about that. So without further ado, Pierluigi, feel free to go. The stage is yours.
Thank you very much for the kind introduction. It's a pleasure and an honor for me to be contributing to this distinguished speaker series that you have put together over the past few years, I guess. Well, today, good morning or good afternoon, everyone. Today, I want to tell you a little bit about my research towards the high assurance design of autonomous and cyber-physical systems, revolving around this rich modeling and specification framework that we are investigating, which is the one of assuming guarantee contracts. Cyber-physical systems are complex integrations between computation and physical processes, but they are evolving, as we know, naturally almost into autonomous systems, which are expected to perform increasingly more sophisticated functions that we used to allocate to humans in the past. And this is in a variety of mission-critical applications, from warehouses to drones for rescue missions to aerospace exploration. Then, thanks to the introduction of modern AI and machine learning methods, autonomous cyber-physical systems are enabling technologies such as self-driving cars, collaborative and advanced robotics, and smart cities. Right? But when we deploy these systems, serious vulnerabilities still are there, right? And they persist. I'm sure that you all have your favorite examples in this domain, right? I am here just linking to a couple of serious, for instance, recalls or a couple of let's say vignettes from recalls from Tesla in particular. This is just something that happened about 1 year ago. And we know that such catastrophic events, sometimes when they happen, or anyway, fatal accident in the autonomous driving domain, tend to erode, to damage trust in autonomous driving, for instance, and in autonomous technologies in general. And while modern AI methods do bring lots of advantages in terms of boosting tasks that were not possible to be performed in the past, they also add additional sources of uncertainty, of approximations of complexity, and raise questions on what could be the foundations for the next generation of design methods to be able to provide stronger guarantees of correctness, safety, dependability for these systems, and even compliance with regulations, especially in areas in which guidelines, for instance, for certifying AI systems are still under development. They're still an open problem, an open topic for discussion. So our take to this problem is that one major challenge in integrating these systems, in building these systems, is really their heterogeneity. From the one side, software and AI functions run on heterogeneous interconnected platforms, including sensing, computation, and actuation. But on the other side, also, cyber-physical systems are built out of the integration of subsystems that are developed by heterogeneous teams, different teams with possibly using different models, languages, and tools that are hardly interoperable. So our approach to tackling heterogeneity in these systems is through a modeling framework, which is indeed contracts, which offer the mathematical foundation and a unifying abstraction, if you wish, to perform integration. It's kind of a layer, it's kind of an intermediate representation that we use. A contract is a model of the interface of a component, and it establishes conditions that make that component, make it possible for that component to be integrated into a larger system, pretty much as a Lego block into the system. Once we rely on these intermediate representations for our tools, for our analysis and synthesis, then we can capture heterogeneous requirements from different domains and transform them into this intermediate representation, which is contracts. And on top of contracts, we could use, and we can use, the state-of-the-art tools from computer-aided design, formal methods, and control to build methodologies that manipulate contract and analyze contracts, synthesize from contracts, optimize, and explore trade-offs. If, for instance, we detect early integration errors, then we can say, for instance, that a set of contracts are inconsistent and provide the reason why this might be the case at the level even of high-level system-level requirements. If instead system-level requirements happen to be consistent, then we could even provide artifacts through synthesis or analysis methods, notional architectures for the system to be designed, or control protocols. This is a kind of end-to-end framework that my team is aiming to, and the first incarnation of this is an open source tool that we are currently also maintaining, Trace, and which was first validated and tested on industrial strength case studies provided by IBM and United Technologies Corporation, which is now RTX. So what are contracts? Right? Contracts are pairs of behaviors. We can assume that these behaviors can be expressed, for instance, by logic formulas or by any kind of formulas. There could be constraints, assumptions, and guarantees. The assumptions are indeed the conditions, the constraints that the component assumes from the environment. In this particular case, for instance, I'm showing a component. Its task is to perform the division between two quantities, two numbers, and the assumptions are expressed as a constraint, as a logic predicate, or in this case, arithmetic predicate on the inputs of the component. The guarantees are instead the promised behavior by the components. And so in this case, they boil down to indeed the functionality that I'm providing, the division between X and Y. Now, assuming guarantee reasoning is not new. It has been there for a while, especially in hardware and software verification. It's shown as it has been shown as a powerful mechanism for, first of all, contextual modeling, like spelling out what is the context in which you aim to integrate your component. These are the assumptions, right? I'm using a pair of models rather than just a model of the system. And moreover, they also provide support for compositional reasoning, for compositionality. Now, recently, there's been some work also showing that they are fruitful and beneficial in cyber-physical systems or mixed signal integrated circuits, and I've been also contributing to this line of work. So the idea is that in a contract-based framework, we could argue about the satisfaction of system-level requirements, for instance, like is suggested by this graph of contracts, by supporting them through a complex composition interaction of contracts, for instance, from different aspects of the system, the safety aspect, the performance aspect, through a well-established algebra and calculus of contracts, where I can say, for instance, the system level requirements are refined by the conjunction of one contract for the safety, safety aspect and one contract for the performance aspect of the system. And then my goal is to try and prove that the safety contract is satisfied by relying on a composition of elements where I have a contract for the sensing architecture and a contract for the planning architecture, and they compose by composition, and so on and so forth. I can stepwise hierarchically refine contracts from a top-level, quote-unquote, goal or system-level requirement up to the leaves, right, of this tree that predicate something properties, pairs also about the components that are involved into the system. Well, this is a nice picture until we include machine learning components in this picture, where questions arise. What is a contract even for an AI's artifact, right? Machine learning artifact. In fact, a specification theory and contracts, in a sense, are a generic specification theory, but customizing such a specification theory for machine learning components is still a challenge, right? An open problem today. Things start to appear, but it's an ongoing debate. Our take is that in order to embrace autonomy, in a sense, we need to also embrace uncertainty and depart from traditional frameworks of contracts that were very effective for hardware and software design, but they were anchored on discrete or even Boolean sometimes notion of satisfiability, yes or no answers, and discrete models most of the time. Instead, what we propose is that contracts should be enriched with support for uncertainty and probabilistic behaviors, and they should be able to support quantification of uncertainty and propagation of uncertainty throughout the layers of your design. And we call this framework, namely this framework of stochastic contracts. It's an extension of contract frameworks to probabilistic and stochastic systems. And indeed, in our view, and they represent a significant departure from traditional frameworks that were, only aiming at yes or no answers, or mostly playing around discrete models. So today, I'm going to give an overview of our recent work in this domain in the attempt of equipping contracts with quantitative tools for performing indeed verification, robust verification, quantitative requirement analysis. And I will first indeed touch upon the applications of stochastic contracts in the realm of verification. I will then go also and talk about also what we are doing in the synthesis domain and design space exploration. And I would like to conclude with a scenario in which we have been using contracts recently also to speed up and somehow help facilitate certification as well, or reasoning about certification artifacts and artifacts about activities, testing, validation of cyber-physical systems. All right, so with that, I'd like to start with the verification part. And let me start with an example, right? Case study, national case study that we want to address and tackle here. For instance, a multi-sensor perception system. We can imagine that we have a system-level contract for this architecture that I'm representing here on the left, where we aim to provide as a guarantee that given that the input distance that we want to measure is bounded, then the output is also an error that is bounded with a high probability. This kind of constraints, right? PAC kind of bounds on the result, PAC bounds, previously accurately correctness bounds on the output of the sensing systems. How can I represent this, right, with the formal specification framework, right, within a formal specification framework? I can also imagine that each sensor here is modeled with their own contracts, right? Also, each sensor has a bound of the probability that can provide and guarantees that the error is bounded with high probability or with a given probability bound. And now my goal is to build a system that satisfies the system level contracts. And by the way, some of the sensors here might be already in my library. They might be given and they are fully specified. I know their properties. They are parameterized by the, for instance, variance of the error, or a few parameters that characterize the error of these sensors. But there are one or more. And here I have sensor n+1, which is kind of a missing component. So it's a kind of a missing sensor that I'm interested in designing, right? So I would like to understand, for instance, what will be the error properties of this sensor, and what could be the optimal noise parameters and cost, because I have also a cost associated to it. And usually, for instance, it's legitimate assumptions to consider the cost as being inversely proportional to the error variance. So then I want the minimum cost or the optimal noise parameters for this sensor, such that when I compose it with the others, and given some sensor fusion also element, where I'm not specifying necessarily what kind of sensor fusion I'm doing, might not be a trivial camel filter, but could be, for instance, some kind of discrete decision making strategy like majority voting and so on and so forth. Well, the composition of the entire system here, one component of which, or multiple components of which, are parameterized, right, with these parameters P and sigma, the probability, the noise variance, should satisfy my system level contracts, or formally I say refine my system level contract. And not only this, right, but I would like also to robustly, quantitatively, as I was saying, refine these contracts. And this robustness margin is rho star in this case. So how can I formalize, right, such a request? How can I specify this kind of requirements for contracts? And then how can I verify this kind of task, right? Or even synthesize the missing components. So that's a little bit the background. And here we have an example mostly motivated from control. We have a power system, a Dreamliner-like power system of an aircraft. This is just a sketch, a diagram. These parallel bars are switches that connect supplies generators to their buses and loads. And the idea is that all the generators, all the power supplies can be failing, right? At least two should be anyway always available. And in spite of all failures, I always have to guarantee that the power is connected with the loads, right? But I don't know exactly the power requirements from the loads at every single time. This is a Gaussian variables. There is uncertainty on what exactly the power is. There are some fluctuations, right, depending on the time during the mission, during the flight. But what I have to guarantee is indeed that all the critical loads are connected. I may want to minimize the load shedding frequency and the switching frequency. I want to shed the minimum amount of load. I don't want to switch too much. Wear and tear, right, is a problem here. And still provide some guarantees on the battery charges, right? I want to be sure that the battery is always has always a minimum charge there. With high probability, the charge level should never be less than 0.3. And if at some point in time the battery level is less than 0.25, then in 5-step at most, it should exceed or equal 0.4 with probability larger or equal 0.95. So this kind of probabilistic requirements I would like to be able also to capture and synthesize potentially a policy, a decision-making policy for the switches to guarantee these requirements. All right, so how do I formalize, first of all, this requirement? I need a rich formal language, and we have been working on towards extending temporal logic languages, right? We have been using in the past, even in Chase, linear temporal logic, or which is already an extension of propositional logic for capturing complex missions, temporal constraints and objectives, such as infinitely often visit region A, never visit region B. But this is not sufficient for cyber-physical systems and for quantitative analysis of these systems. We then moved progressively to signal temporal logic, where we interpret the predicates over continuous valued signals. We are able also to state properties like the barrier charge level V shall be less than 5 at all times between 0 and 10, right? This G means globally, always between 0 and 10. V should be less than 5. And not only this, but because we can reason about continuous valued signals, we also can estimate, we can also estimate the distance with respect to the threshold here of 5. And so the margin by which we are satisfying, or the negative margin by which we violate a specification, that's also what we mean by robustness in this case, and by quantitative analysis of these systems. But we haven't gotten to the probabilities as yet. So what we've been proposing, and we have been experimenting with, is an extension of signal temporal logic to also support probabilistic predicates and chance constraints. So for us, then, contracts are a pair of stochastic formula specifications in stochastic signal temporal logic, which enables also predicates such that the battery charge level B should be at least 0.3 with probability at least 0.95. And this, for instance, to hold always between in an horizon between 1 and 20, something like that. And also, importantly, on this logic, so not only we add let's say, quantitative modality in terms of supporting probabilities. But on top of the probabilities, we can also support a robustness notion. We can also we have also quantitative semantics where we define now margins, not anymore between signals and the threshold, for instance, that we want to keep, but we rather measure, for instance, now distance in probabilities, and we establish robustness margin on distributions and on probabilities. So every predicate has associated its robustness estimate that tells not only whether the predicate is satisfied or not, but whether we have a positive margin and how much, or negative margin of satisfactions on the probability. In this case, for instance, I'm showing there is a margin of 0.28 of robustness with respect to my request that the probability be larger than 0.7 for this kind of distribution and cumulative distribution. All right, so if I have this logic formalism now, can I lift this to stochastic contracts, right? What kind of problems can I solve now by using pairs of formulas, one specifying what the assumption should satisfy, and the other the guarantees of the component under those assumptions? So let's go and check, for instance, what is a typical verification framework for contracts. This is a scenario in which you have a system-level contract and an architecture made up of two components, right? And my goal is to use these two components to satisfy the system-level contract. And what I'm going to do now is indeed, first of all, right, I would like to reason about allocation of requirements to the different components. How can I optimally split the system-level requirements C into two contracts, C1 and C2, and my goal there is to show a refinement relationship, right? It's a pre-order, partial order relation between contracts. And my goal here is to show indeed that the composition of C1 and C2 refines C. Now, since contracts are pairs of logic formulas for the purpose of this presentation, I can also frame the refinement relationships between assumptions and guarantees using these chains of implications between formulas, modeling the assumptions and the guarantees of the single components, as well as the overall contract C. And these are the chain of implications that I want to be satisfied and I want to check in a verification process. Another problem in verification with contracts would be then to see, once I have allocated, right, the different requirements to the different components, C1 and C2, my question is whether, for instance, M2, right, satisfies a contract C2. By the way, here I have a pictorial view of refinement, right? What I'm saying with this chain of implication is that in order to refine an high-level contract C, what I'm asking to the composition C1 compose C2 is that the guarantees are stronger, right? And the assumptions are weaker in a sense. So meaning the top-level contracts has broader, wider guarantees and smaller assumptions that the bottom level, more concrete contract made up of the composition of C1 and C2. So in order to refine a contract, I need to strengthen the guarantees and weaken somehow the assumption. And there is also indeed logical formulation for the satisfaction task, right? Where the goal is to prove that a component M2 satisfies C2, and this is also this chain of implications there. Now, this is the world, let's say, in a quantitative modality, right? In a qualitative modality, sorry, where I'm only aiming to a yes or no answer. But what I mentioned before is that indeed I'm really interested in a quantitative framework instead. And so, and in particular, also probabilistic. So what we proposed is indeed the extensions of this verification task to also encompass robustness requests, right? So I can then compute by using the semantics of the implications and also the semantics of STSTL, I can associate also to complex logic formulas and combination of STSTL atomic predicates, right, which are chance constraints, probabilistic constraints, robustness measures, robustness estimates. And then my goal is to reframe, right, those checks implications, right, that I had in the previous slide now, but by computing the robustness of them and by making sure that that is, you know, larger than raw star, for instance, in this case. So I see that there are some raised hands and
yeah,
some
maybe
questions.
it's a good time. It's a good time to ask some questions. I think
Sure.
there were some questions in the chat, and then Scott had ends up. So let's first start from the chat. So there was a question from Subrata on the previous slide, or actually also on this one, the system architecture. I think the general question is: are you thinking of the system architecture to be modular in nature?
That's a good question. I think in many cases, right, in order to argue, even in certification for certification agencies, certification committees, and so on, I think it's very useful and beneficial sometimes to think about already architectures that are modular. And many times, cyber physical systems, from hardware or software systems up to potentially, you know, avionics systems, aircraft systems, are built in a modular way, right? As they are system of subsystems, where many times each subsystems is built by a different team, by a different group. So we want to kind of support those scenarios, right? But definitely, for instance, we have been thinking about architectures that designers believe they are modular, but they exhibit emergent behaviors, and then how to quote unquote model also those characteristics, probably, you know, components that don't behave so much as modular as we wished. They could be lumped together and called, right, as a new component with emerging behavior. So we are interested also in studying these cases, but that's a good question. And yes, for the moment, we can think about component-based architectures that we want to support.
Great. And the follow-up question from Subrata was regarding this slide. What is the metric of robustness to obtain highest guarantees? You talked about refining these contracts, and what is the particular metric you're using?
Right, we will have some examples, right? So these are really margins with respect to the predicates of the logic, and so it's not really a metric in the sense of metric in topologies. In this case, it's more like a difference with respect to the the thresholds, or for instance, let's assume that the predicate in a chance constraint is linear, right? For instance, the voltage lower, like for the battery level example that I had before, the battery level lower than 0.5. So it's going to be the actual battery level, how far is from that kind of threshold. So far, we start building on top of that. But then, of course, we have OR and logic combination of these distances, and we combine them through minimum and maximum to get an overall robustness measure. So we don't have still a topological space, a classical measure on that. This is open, by the way, and having smoother measures might help a lot. Now, in terms of what is the actual, raw star that might be interesting, we rather want engineers to be able to explore those margins, so to play with that, to do what-if analysis, counterfactual reasoning by putting together these models and redoing validation, verification, and determining, elicit somehow what are the good margins that are compliant with your intent.
Great. Thank you, Pierluigi. I think the question Scott had was a mistake. So it doesn't seem we have any other questions.
Yeah,
so
thank you. I'll then proceed, and happy to anyway respond to all the questions that come. All right, so we have done a robustness definition. By the way, this was not there, right, in standard contract frameworks, and it's been one of our contributions in extending this. But now, of course, we need to also compute, right? So how do we frame, do we encode these constraints? How do we solve these verification problems once we have formulated them, right? And what we could show, this is also, by the way, an open problem. And by the way, STSTL is our first attempt at formalizing stochastic contracts. There are also other interesting probabilistic frameworks we were also exploring. But in this particular case, we found out that a fragment of STSTL, a bounded time fragment, on certain categories of systems that we'll mention in a while, is indeed, can bring to problems that we can decide. And in particular, we can encode formulas, bounded time STSTL formulas, into a set of constraints on a finite horizon that establish necessary and sufficient conditions for the satisfaction of either the assumptions or the guarantees. And by building up both in the quantitative and in the qualitative framework, right? And so essentially, we can also transform these probabilistic constraints actually into deterministic constraints. So it's a kind of determinization of the chance constraints. But now the constraints are on the probabilities, on the distributions of the system states. And we can reason on the probabilities on the distribution using deterministic problems instead. Now, many times these decision procedures that we create are just semi-decision procedures. So they are sound, but not necessarily always complete, and because they indeed create either under or over approximations. Whenever they complete a task, we rely on those to be sound, but whenever they conclude with unknown, we need to go backtrack and refine our approximations in order to solve the task, right? So it's a kind of paradigm that includes an iterative abstraction refinement procedure of our constraints. But the bottom line is that this implication of formulas lead to a set of constraints that establish necessary or sufficient conditions, and the feasibility or infeasibility of these constraints tell us whether, for instance, C1 refines C2 or C1 does not refine C2. Similarly, we could, for instance, ask whether a stochastic contract is even feasible, right? Has an implementation. So in contract-based terminology, we say that contract is consistent, or or rather it is inconsistent, right? It doesn't exist in implementation, right? I compose two contracts. My first question is, there's going to be any component that satisfies both, right? That or I combine in somehow. And this is a consistency issue. And also for those, we have this kind of sound semi-decision procedures and consistency checks that we frame as deterministic optimization problems, right? This is in the case of qualitative verification. By the way, many times this reduced for linear predicates in STSTL into MILPs, right? Mixed integer linear programs that combine both the logic structure of the formula with the probabilistic structure in the linear and the linear predicates of the STL, continuous and probabilistic structure of the formulas. We need a formalist that encompasses both. Of course, relaxations, right, to convex programs are also in place, but of course, there is a trade-off between accuracy and soundness and cost, right, computational cost. In this case, I'm showing how I transform also a robustness satisfaction problem, robustness consistency problem. For the robustness check, right, I want to check that robustness is larger than a certain amount, a certain margin rho star. So what I have to do here is to solve essentially an optimization problem to find the minimum rho that satisfies all the constraints, the minimum robustness distance, and check that that is larger than a certain threshold that I want. Now, this encoding has been effective so far for a few classes of systems, so practical relevance. We applied this to linear system with measurement noise, also systems with additive and control dependence, so there is also a multiplicative term there, Markov jump linear systems, and similar. We are now extending actually and thinking about extending the domains like that can benefit from this formalism and on which we can compute actually verification and synthesis tasks. So this is the framework, right, for verifying stochastic contracts and in particular robustness of refinements and satisfaction. Let me get a little bit some details into how we frame also synthesis problems, which we believe are important for design space exploration. I will give you also some results on the two case studies that we saw and argue a little bit about certification. So how do we frame a synthesis problem, right? This is kind of the reverse of the robustness verification. Now we have a component in gray, which is parameterized by a set of parameters phi. And our goal is to find the contract, even find the spec, right, the requirements on that component in gray, such that when I compose C2 with C1, the contract for the gray component with C1, then I robustly refine the system level contract C. Similarly, I can pose robustness satisfaction task where indeed I'm looking into parameters for the component M2 to robustly satisfy now a spec, which might be also parametric. So I might be able to relax also the requirements if I don't find, for instance, a component in my library and so on and so forth. So this is a synthesis problem. But now indeed I'm adding one more level of complexity on top of the verification because usually this kind of synthesis problems where I want to minimize the parameters, they kind of generate bi-level optimization problems, since I first want to make sure that over all the behaviors, the robustness constraint is first satisfied, right? And then on all the parameters that guarantee that the contracts are robustly satisfied, then I find those ones that also minimize my cost. So I have to solve a minimum over the parameters, but also minimize over the finding, the worst case behaviors as well. Now, we solved heuristically at this moment. It's not always easy to transform these problems into just single optimization problems, but we also put in place strategies that are based on heuristics and discretization of the state space and nested optimization strategies to solve in a nested fashion, iterative fashion, these kind of bi-level optimization problems. So let me now go and tell you a little bit about some of the results, for instance, that we could achieve, right? In this case study of the missing component, we framed the robustness verification problem, but also the synthesis problem, where we want to find sigma and p, the parameters, the specification, and the standard deviation of the missing components. Right? We showed that we could effectively explore trade-offs between, for instance, uncertainty and redundancy in this kind of multi-sensor systems, right? So how many sensors do I need, for instance, to achieve the specification, given some constraints on the cost that I can afford, or I want to minimize the cost given some constraints given by my library of components. And I could find, for instance, that as the number of sensors that I, of course, admit increases, then I can typically choose sensors that cost less and that they give me also a higher, larger standard deviation of noise. But the interesting thing is that I can quantitatively really determine, right, the margin that I have, how much margin do I want, what kind of sigma do I need, what kind of spec do I need if I have to buy or make that sensor, in a sense. And all of these, even with hundreds of components here, could be done by generating MILP problems in about 20 minutes. For the control case study, we essentially came up with schemes to synthesize stochastic model predictive control strategies for the aircraft power system. And this is, for instance, an example where we show how the requirement that eventually the battery should exceed at 0.4 if at some point in time it's less than 0.25, right? Could be validated after the fact. We first synthesized the strategies, and these are only 50 simulations. Of course, this is not a statistically relevant samples, but we have also plots and and validation with more simulations where we performed Monte Carlo to show indeed that with the confidence that we wanted 0.95 in this case, we really satisfied this kind of complicated, right, articulated, bounded reachability and safety constraints, right, that we pose on the battery charge. And in fact, actually, we show that we can enable efficient automatic generation of control policies using stochastic MPC strategies here for a richer set of specification than previous solutions that were just manually encoding these constraints. Right here, the encoding comes directly from the contract, so it's a synthesis process, which we also put on open source in this PyCasse tool that frames for you, given the system level contracts, the problems and then solves them. All right, so we have seen how contracts can be useful, and there in particular how it is beneficial to consider probabilistic extensions to reason about uncertainty and synthesize control policies with guarantees, probabilistic guarantees on the satisfaction of logic constraints, logically framed requirements. We have seen indeed that contracts are nice contextual models that allow you to predicate whether in a certain context you can integrate a component. They are now ready to embrace uncertainty through probabilistic formalism and combine nicely logics with probabilities, right? Logics with probabilities and also automata-based formalism, I should say. In another line of work, we also showed that. Now I want to claim that contracts could be actually used even broadly to also not only predicate about safety or liveness or properties about the system, but also about the procedures that we use to certify a system, to verify a system, to validate a system. In a sense, they can kind of offer a semantic foundation for building arguments about the correctness of systems. And that's what I like to devote to the last few minutes of my talk today. And I want to remind you how tough is certification, right? How costly it is. And many times companies are fighting against, producing small changes in their product would turn into completely recertifying the product, right? Or anyway, it's a fixed cost that it's not always easy to undertake. And current standards even, right, they don't, for instance, support new technologies like modern AI systems, right? So there are many cases in which standards are not there, and prescriptions of a checklist, let's say, of measurements and validation procedures is not in scope, right? So then our idea is, why instead of sticking to a checklist, don't we really aim at gathering the necessary evidence and using instead the properties and the evidence that come from the validation, the development process of a product as a basis for certifying the product itself, rather than just checking whether A, B, or C have been done, right? And so, this is also an idea that has been pushed by NASA and the FAA, and they are actually promoting the idea that one could build rather customized arguments for certifying systems based on what they call the overarching properties of a system. Like, does my specification comply with my intent? Correctness is, does my implementation correctly refines or implements my specifications, right? And innocuity is, does the system show or exhibit any behaviors, undesired behaviors outside of the ones that I specified? So why don't we use these overarching properties and we instantiate them in the concrete context of a product to gather evidence and insights for certifying the products, right? In fact, there was a DARPA program, Automatic Rapid Certification of Software, that was advancing the importance of evaluating evidence using assurance cases. I'm using here a quote from a standard, the Code Structure Integration Standard, which defines assurance cases as compelling arguments. You can see here a pictorial representation of an assurance case. And the idea is to bridge a certain conclusion with a pool of evidence about a system, about a service or an organization, and showing that it will operate as intended based on the evidence, right? In a context, right, defined by the environment in which I'm using the system. Now, assurance cases have started to kick in, and many companies right now, right, they are engaging in conversation with their customers, right, by showing, for instance, that indeed you can make an argument about, or you can attempt, right, to use this notation, for instance, to argue about the safety of, in this case, self-driving vehicles from Aurora. Right. This was a conversation that started in Uber some time ago, and Aurora brought it further. But this, this kind of semi-formalized argument might become pretty massive, and they still use natural language, which is not so formal, right? They are prone to ambiguities and especially prone to confirmation bias, which is something that humans are sometimes, subject to. So our question here, especially if we want to build this kind of arguments, right, in a more systematic way, if we want to not only build them, but rebuild them as the knowledge about the system changes, then we should be able to formalize them and use design automation methodologies to automatically create them and generate them. And that's exactly what we undertook under this DARPA program. And think how we formalized indeed claims in an assurance case. Well, we formalized them as contracts, right? Where now the claim is indeed the guarantees, the promises, right? And the context in which the claim is made is represented by the assumptions. And now the contract is also a predicate about the certification approach that we are using, the testing, the procedures, right? And how about a claim being supported by another claim? Well, this is refinement of a contract from another contract, right? In a certain context, we call it conditional refinement, right? And what if a concatenation of claims supports a top-level claim? Well, this is a network of contracts with composition operators that refines a top-level claim. And so what is then an assurance case? An assurance case is a hierarchical network of contracts, right? Now, if I were in an ideal world, I could prove then the refinement of these contracts, right, from the top level goal to the evidence, and I would have a logical way of saying, right, oh yes, I'm done. The system is safe, right? The system is airworthy. But unfortunately, we are not in an ideal world, right? At the very least, we have epistemic uncertainty on almost every many steps, right, of this process. Not actually almost every step, but many steps, especially the evidential steps, the steps that are mostly linked to evidence, right? Which are usually the leaves of this tree of contracts. And so the idea is that we indeed have uncertainty in how long we needed to test the system before predicating anything, right? Or whether, for instance, a formal model is a good one, right? Is faithful enough. For instance, even if model checking, right, has provided me with the most exhaustive guarantee on the satisfaction of a requirement, well, I should still go and analyze whether the models that I use for model checking are trustworthy, are responding enough sufficiently to the real system, right, are compliant, are consistent with the reality. And so we essentially pair an uncertainty quantification methodology to these contra networks. We use Bayesian belief nets to represent uncertainty in this case, and the confidence that we have in certain procedures, measurement procedures, testing procedures, usage of formal methods. And we kind of extrapolate and first elicit the confidence in these Bayesian nets, and then argue about the confidence as we compose these contracts. So that's where we also use a stochastic formalism to also predicate about certification artifacts, as well as the confidence that we have in them. All right, so in the interest of time, I will just show a big picture of how we put all these pieces together and some results that we obtained in this program. So we indeed created a framework in collaboration with Collins Aerospace and RTX Technology Research Center, where the performers in this program. And we create both tools and that communicate together for generating assurance case candidates out of a library of patterns, assurance patterns. Our take is pretty much in the same way there are patterns for programming, we should have also assurance patterns. And assurance cases should come up in a certain way modularly and compositionally from these patterns. And that could be reusable across different systems and across different properties that I want to predicate about the system. And after I generate a set of candidates, there are possibly many ways of complying with a certain for instance, claim, then I also evaluate them. And I might have different claims with different strength. And I might choose the one that is most compelling, for instance, to me, of the ones that I have the best evidence, quote unquote, right, based on my confidence on the evidence, on whether I mitigated the risks upon deployment. And so that's where the validation, uncertainty quantification parts comes up. So we put together algorithms based on graph and refinement checking for picking from a library of arguments the argument that refines a top-level goal. In this way, we can hierarchically and modularly build hierarchical contra nets. These hierarchical contra nets are then evaluated based on the Bayesian nets, the models of uncertainty that we have. And if the confidence that we have in the different contracts is high, sufficiently high, we use some rule methods here to decide, right, the threshold, then we propagate that confidence upward in the argument from the leaves up to the top level claim, and we come up with a confidence or a level of strength or persuasiveness of the argument that is being created in this way, you know, in spite of the epistemic uncertainty that is in the system. And we show that our modular approach based on contracts is indeed pretty scalable in this case. There were previous proposals were kind of lumping the entire assurance case as a unique full uncertainty-based, you know, Bayesian net, massive Bayesian net. well, these kind of monolithic approaches show limitations in terms of scalability. Instead, our validation approach that uses only local Bayesian reasoning at the level of the leaves, and then a logically driven propagation upward from the leaves to the top level claims, show instead that that we can reach, even validating astronomical number of candidates in a case study that was motivated by an industrial aerospace system in a decent amount of hours. So these are just screenshots from the tool that we built with RTX, where we show here, we visualize the patterns, the assurance patterns, both in natural-like language, like English-like language, and graphical language as well. And we, for instance, tested this framework in addition to the industrial aerospace systems that I was talking about, also to open source platforms like the Ardocopter from the Ardopilot platform. And we have kind of evaluation data as follows. For instance, 80 candidates could be including, for instance, 24 refinement steps, right, could be generated in 12 seconds. And even a billion of candidates in the industrial aerospace system, right? This was a security assurance case where there were really multiple ways, from static analysis, architectural analysis, and model checking, and to also different kind of controls, security controls that could be used in the system, right? There were really many, many ways to mitigate uncertainties and to mitigate potential vulnerabilities. And we could generate billion of candidates, right? And validate them in something like 30 minutes or so. These are interfaces that we were using, by the way, leveraging the previous logo of RTX, right? It was Raytheon Technologies here. And we show, for instance, that not all the candidates pass. We can say which one pass because we have sufficient evidence, which one instead are no longer supported or cannot be supported. But we also say what are the missing evidences that would make a case, right? It would be helpful, for instance, to argue about safety or security in this case. So very good scalability results, and also pinpointing what is missing, like in this red claim, right, that we see it's not supported by sufficient evidence, and we can pinpoint also graphically as well as in text mode what is going wrong. So I'll conclude here in the interest of time. I hope that I provide an overview on how contracts can indeed offer a formal foundation towards assurance design, both at the level of verification task, synthesis task, but even helping systematic reasoning about certification artifact as well, in a way that could be done many times in a parametric way and updated on the fly potentially, right? Thanks to automation and to this modular view, as we build more knowledge, we have more knowledge about the system. So towards a continuous certification paradigm. Now I'm gonna just show very quickly, right? We are just scratching the surface. There are so many other problems that we wish to tackle with contracts. And for instance, we do have efforts in my group looking at combination of contracts plus learning, in terms of both using learning to learn contracts, as well as using contracts to guide learning and constrain learning. We have, in fact, some logically constrained decision-making also approaches that try to use logics to guide or even constrain reinforcement learning, for instance. At the level of assurance cases, we hope to be able to scale further this framework to be able to make trade-offs between assurance and cost, right? To find systematic way to elicit this kind of assurance patterns that I assumed in my framework, right, in our framework, and these confidence models towards, an agile continuous assurance approach using principal aggregation of heterogeneous evidence. I stop here and I thank, of course, all my collaborators, my students, many of them already graduated that are in this slide, and collaborators, and of course, agencies that have been supporting my research. I apologize for the time that I exceeded, and yeah, be happy to take some questions.
Thank you very much, Pierluigi, for the great talk. Very, very cool how you're working on different aspects of these problems. Very interesting. So let's take some questions. You can either write in the chat or raise your hand. There were already some questions in the chat. So I'll start by those. So Subrata asked, at some point you were presenting these various viewpoints from NASA, DARPA, and so on. And at that point, Subrata asked, what are the present standards? Who is the authority today that governs these things? And I think an interconnected question is, what is then the role of insurance companies in the whole process, for instance?
Well, I've not investigated so far. I've not thought a lot about insurance companies in respect, but I expect, they will benefit as well from a more principled, evidence-based, right, and not only checklist-based approach. In terms of agencies, we interfaced a lot with NASA, indeed, and FAA, because this program was mostly motivated by avionics, software and hardware platforms. There were, performance in these DARPA programs were essentially all the defense subcontractors, right, in the US. I don't, name all of them, but they were named my collaborators from RTX, but they were essentially all there. And the idea is, but even, in the nuclear domain and so on, people are looking into more systematic approaches that you can argue. In fact, in this very animated debate sometimes with people, from argumentation, theory to safety and so on. We were even asking ourselves whether the standards that exist out there, right, could be reverse engineered and prove, for instance, that if you comply with the standards, you are safe. So, and this was, an open debate there. Even sticking to the standard doesn't potentially guarantees, right, safety and so on. So one way to start, right, in systematizing these systems is indeed to encapsulate knowledge, right, that has been accumulated in standards so far. And so there are standards from avionics, right, the 178C, the 333, right? But the point is to go also beyond those, right? Also, because for AI, for instance, right, we still, the guidances are still appearing, and Europe is, in a sense, even ahead, right, in this domain now with respect to the US. But the idea is, can we then use and reuse, right, this framework to argue more systematically and probably come up with the next generation standards there?
Very nice. Thank you, Pierluigi. So there is a question by Christian. Feel free to go ahead.
Hello, can you hear me?
Yes.
Yeah.
Hello, thank you so much. Very interesting and cool presentation. I have a more of a general question. Do you have experience with actual experimental data or experiments that you are doing in your lab or collaborating? I am talking because I work in a project and we use cyber-physical systems, but in a more, not hardware in the loop way, but more hybrid simulation type of way. So we have a computational instance, we have a lot of experimental components, and we generate a lot of data, especially focused on space habitats. And some of these techniques are very interesting and are things that we are currently trying to look into. But I just wonder if you have any experience with other types of experimental data that you may be willing to comment about. Thank you.
Well, I would be more than happy, for instance, to cooperate with people that are more on the experimental side. So in my experience, so most of the work that I have presented in these slides today is more a computational kind of work, right? In the sense that the quest here was towards exploring, the boundary between what is computable and what is not, right? As you try to put more expressiveness into the language that you use, right? And now let's augment it with the probabilistic predicate, and now let's augment it with the robustness on the probabilities. The effort was to build a richer and richer language and see how much I can still say, right, about the system. So that was the challenge. But that said, all of this is totally applicable in a simulation-based approach, right? In fact, I could use this kind of stochastic temporal logic and signal temporal logic to build monitors for data, to monitor this data. And I could use this data to even learn the distributions that might happen and build these probabilistic predicates now with a more grounded, substantiate, right? These parameters that I talked about, rho, delta, and so on and so forth. And so I've done a lot of this in my also, previous life as a circuit designer. I've been building chips where, SPICE was in analog, especially. In particular, I built mixed signal designs where I had both, a totally synthesized component, like a digital portion of my chip, and a component, an analog, component that I had to simulate with SPICE. So I'm totally also aware of the problems that arise in that and the importance of that part, which I indeed skipped in this presentation because I consider that, and by the way, right, even in this assurance case framework, the name of the game there is how to best combine testing or simulation in the loop or hardware in the loop, even emulation, right, with the formal methods to get to kind of cost-effective arguments, right, that might let you say, for instance, I tested for 10 hours, but because I did this model checking, I'm confident that this is sufficient to at least first deployment of the system. So it's really about combining carefully coverage measures and testing and requirement-based testing with formal methods, the name of the game, also for the future for AI. And so, yes, so I have experience in hardware design. I have also some internal experience from Raytheon. Right now, for instance, the DARPA program just completed in February, and they are now spinning up some kind of internal technology transfers internal projects in which they're essentially pairing the assurance case framework with a digital twin of a system that they have. So they have the data, they have the framework, and they have the digital models somehow. And so they can support the assurance case with their digital twin. And so they can build arguments that are based on what they can infer from the digital twin. So that's, in my opinion, really an ideal scenarios to really validate these techniques and these methods. So I think this is something that they can do. And I still, being a non-citizen, cannot entirely always support. My student is going to join them for an internship this summer, and he is an American citizen. And so, but I'm totally, more than interested, I would say, in pairing with people that, for instance, have a sufficient amount of data to push this further and so on. So I hope, that a sanitized case study can come up from Raytheon as well, and I would like to collaborate with them in this domain, but that is really welcome. And I have so many problems that we could test on such a platform.
Thank you. Thank you so much.
Thank you, Christian. Is there any other question from the audience? Oh, yes, Scott, go ahead.
Thanks. Great talk, Pierluigi. So it seems like there was an emphasis where you already have a product and some assurance cases, or a company is already more advanced in their stages of development. Have you thought some about earlier stage development? Say a company is just building prototypes, they're starting to do some scenarios, they're collecting data. So they already have some models of what they think is important. Like they have scenario, maybe they have a scenario description language. So have you thought some about this, or is it like a direction future work?
That's an excellent question. And no, that's actually the reason why we wish to automate and we wish to systematize also the assurance case framework, because we believe that so the benefit of automation sometimes is not just apparent in the duration of the life cycle. I come from a background in electronics where really the time to market is limited, right? Of course, now this is happening also in other, segments of industries, including avionics sometimes, right? Shortcuts are taken in order to go faster on the market. Now, but okay, everybody can agree that the time that it takes to develop an aircraft is not quite as, comparable with the, this kind of scalability results that we wish to have here, the alpha hour and so on. But the idea is really to be able to do this many times, to be able to model the system, even by using, linear temporal logic contracts at a very high level and high-level models just at the conceptual level. And then as we wish to integrate more knowledge from the system, in fact, actually what we believe, especially for embracing AI and autonomy, we may not want to just, deploy it based on, oh, okay, the top level goal says it's airworthy, right? But even, by using an idea of pretty much as sometimes vaccines get first deployed on a smaller community and then extended to a broader, and similarly, probably autonomy is kind of seeing this kind of paradigms, right? Or even in flight tests, right? People decide how many hours of flight tests they need before they bootstrap more confidence about then really deploying the system more and more. We do believe that indeed this is a framework that helps, where you could go back and annotate your contracts or update your Bayesian nets that estimate the confidence that you have, or learn about a new procedure, for instance, a new static analysis procedure that allows you to conclude whether that security vulnerability still exists or not, right? We studied this, with all the possible CVE and CWEs also in software and hardware, and we incorporate that. That's where the billions sometimes of candidates come from in these industrial case studies that we analyzed. So, and we believe, that the potential is even stronger in that part, right, of the when you are really in the acquisition process of a system, where you want to validate the concept as well and avoid late decisions, right, that may be really expensive. Thank you, Scott, for the question.
Thank you, Scott. Any other final question for Pierluigi? Okay, doesn't seem so. Pierluigi, was a great talk. I think the topic is super interesting and there are so many things to do, as you say. So looking forward to seeing this develop in the next few years. So thank you again for the talk. And thank you everyone for joining. And I look forward to seeing you next week for the next Autonomy Talk.
Thank you, Joelle. Thank you, everyone. And have a nice rest of the day.
Thank you, Luigi.